In this tutorial, we'll be discussing the empirical formula and how it relates to the percent composition. So, with the percent composition, it tells you the percentage of each compound and how it relates to the bigger picture. For instance, if we look at NaCl, sodium chloride, how much of the compound is just sodium, how much of it is just chlorine. Or if we look at water, how much of it's just hydrogen, how much of it is just oxygen. So let's say, for instance, we're given the reverse. Instead of determining the percent composition, we actually have the percent composition. We're trying to figure out what compound it is. It is possible for you to go back and forth that way. However, it's not going to give you the complete compound. What it's going to do is it's going to give you the empirical formula. What the empirical formula is it tells you the smallest whole number ratio of the atoms in the compound. So for instance, if we look at hydrogen peroxide here, it's H2O2. The empirical formula of that is just HO. It can be reduced down. Another one that you can look at is C6H12O6. That's sugar. You can actually reduce that down to just CH2O. Let's write that better. CH2O. Alright, so the empirical formula is the most reduced form, whereas the molecular formula is not. It is possible for them to be the same, but not always. Alright, so there's a little rhyme that you can remember to remember how to get the empirical formula from the percent composition. And it's right here on the right hand side. Percent to mass, mass to mole, divide by small, multiply to a whole. So what that means, you have a percentage sign here. You're going to change that percentage sign to grams, percent to mass. That's all there is to it. So instead of 72.2% magnesium, it's 72.2 grams of magnesium. Alright. Percent to mass, mass to mole. Well, to go from grams to moles, you know that you're going to use the molar mass. So here's magnesium, 24.305. So there's 24.3 grams of magnesium in every mole of magnesium. So percent to mass, mass to mole, that gives us 2.97 moles of magnesium. Alright, so let's do the exact same process, but now with nitrogen, because we can't divide by small until we have all the elements here. So we have 27.8%. We're going to turn that into 27.8 grams of nitrogen. Percent to mass. Mass to mole, 14.0. So 14.0 grams in 1 mole of nitrogen. That becomes 1.99 moles nitrogen. Okay, so we have percent to mass, mass to mole, divide by small. What that means is you're going to look at the two numbers. You have 2.97 and 1.99. The smaller of the two is 1.99. So we're going to divide both sides by 1.99. And essentially what we're doing here is we're getting a ratio of magnesium to nitrogen. So this comes out to be 1.5, and this comes out to be 1. So for every one nitrogen, there's 1.5 magnesium. Problem is you can't have half of a magnesium atom. So what you're going to have to do is you have to get rid of that 0.5. Figure out what fraction that is and multiply by the reciprocal. So 0.5 is the exact same thing as saying 1/2. So we're going to multiply both of them by 2. So the actual compound says we have Mg and we have N. 1.5 times 2 is 3. And we have 1 times 2, which is 2. So the compound is Mg3N2. By doing percent to mass, mass to mole, divide by small, multiplying to whole. Let's try another one. A compound is found to have a percentage by mass of 48.38% carbon. So that means 48.38 grams of carbon, because we're assuming there's 100 grams here. That gives us percent to mass. Mass to mole, we look at carbon, 12.0. That comes out to be 4.03. Then we have 8.12% hydrogen. That means 8.12 grams of hydrogen. Hydrogen's right here. So in every 1.01 grams is 1 mole. And that comes out to be 8.12 moles of hydrogen. Now it says here the rest of it is oxygen. So we have to figure out how much oxygen is here. Remember, this is out of 100 because it's a percentage. So we can add 48.38 plus 8.12 and subtract that by 100. So 100 minus 48.38 minus 8.12. That tells us that we're going to have 43.5 grams of oxygen. That's how you figure out how much oxygen you have. Now we do percent to mass, mass to mole, 16.0 grams, 1 mole. That comes out to be 2.72. Divide, so we have percent to mass, mass to mole, divide by small. We have 4.03, 8.12, and 2.72. The smallest is 2.72, so that's what we're going to divide by. Obviously, this cancels out to be 1 for oxygen. Hydrogen is approximately 3, and then carbon is going to be approximately 1.5. Once again, we have a half there. So to get rid of the half, we multiply everything by 2. So that comes out to be CH. Oh, I ran out of room on the bottom, so I'm going to put it on the top. So 1.5 times 2 is 3. 3 times 2 is 6. And 1 times 2 is 2. So C3H6O2. We'll do one more like this. A compound is found to have 46.67% nitrogen, 6.7% hydrogen, 19.98% carbon, and 26.65% oxygen. So this is going to be a longer one, but keep in mind the pattern is always going to be the same. So let's start from changing everything from percentage to grams. And then after that we convert everything to moles. So 46.67 grams of nitrogen. Convert that over to moles by looking at nitrogen is 14.0. And that comes out to be 3.33. Then we have 6.70 grams of hydrogen, 1.0 grams because of the molar mass, comes out to be 6.70 moles of hydrogen. Then we have 19.98 grams of carbon. look at the molar mass is 12.0. Divide that out, and it comes out to be 1.66. And finally, we have 26.65 grams of oxygen. Molar mass is 16. 26.65 divided by 16 comes out to be 1.66 again. But now this is oxygen. So, percent to mass, mass to mole, divide by small. We had to figure out which one's the smallest. We have 3.33 for nitrogen, 6.7 for hydrogen, and 1.66 for both carbon and oxygen. So 1.66 is going to be the smallest. So, carbon cancels out to be 1. Oxygen cancels out to be 1. 3.33 divided by 1.66 is going to equal 2. And 6.7 divided by 1.66 is going to equal 4. So that means I'm going to go to the top again up here because I ran out of room. Nitrogen, hydrogen, carbon, and oxygen. I have 2 nitrogen. Multiplied to a whole we did not need to do because there was no fractions here. Hydrogen is 4, carbon is 1, and oxygen is 1. You can leave the ones off if you want, so it'd be N2H4CO. Once again, because I didn't have a decimal at the end, I didn't need to actually look through and figure out what to multiply it by. Alright, so calculating an empirical formula from experimental data, you're going to think about it in the exact same reference. So let's say we decompose a sample of water in the lab and find that it produces 3 grams of hydrogen and 24 grams of oxygen. So how can we get the empirical formula from this? Well, since we're already given it in grams, this percent to mass has already been taken care of for us. So we just skip right down to the next part of mass to mole. So 3.0 grams of hydrogen over 1. The molar mass is 1. So 1.0 grams in 1 mole. That's going to equal 3.0 moles of hydrogen. 24 grams of oxygen. Once again, they already have it from percent to mass for us. We just go from mass to mole. Put that over 1. Oxygen is 16. So 24 divided by 16 is 1.5. So we have that figured out. Divide by small. 1.5 is smaller, so we're going to divide both sides by 1.5. This comes out to be 2. This comes out to be 1. So multiply to a whole, the numbers are already whole. So H2O1. So H2O. Alright, so this is just basically a summary of what we've already talked about. The first step, percent to mass, assume that there's 100 grams there. So by just changing the percentage sign to a gram sign, you've done that. Convert each of the masses to the moles by using the molar mass. Then you're going to divide by the smallest number, so that way you can get whole numbers. And then you're going to multiply. Step 4 gives you the ratio. Step 5 gives you the whole numbers. Alright, so if you're given a subscript, or if you have a decimal place, for instance, we have 0.5 there several times. We had to multiply it by 2. This chart helps you realize what number you're supposed to multiply everything by. It's just a little cheat sheet. If you think you might have a problem with this, then you might want to take some time and look it over and see how it's worked out. But it's very simple if you look at it as far as the fractions. For instance, 0.25 is the same thing as 1/4. The reverse of that is 4. 0.33 is the same thing as saying 1/3. The reverse of that is 3, the reciprocal. That's how we got to that too. Alright, we're going to finish up this tutorial with one last example. Alright, so calculating the empirical formula from an actual data reaction set. 3.24 grams of titanium reacts with oxygen to form 5.40 grams of metal oxide. What's the empirical formula of the metal oxide? So, when we're looking at this, we notice that it reacts with oxygen to form. So this is the titanium and the oxygen combined. So how much of that is oxygen? We have to subtract it out. So we know we have 3.24 grams of titanium. We do 5.40 minus 3.24 to figure out how much oxygen is there. And that comes out to be 2.16. Now we're going to convert them to moles. So we figured out the masses of each. Mass to mole, titanium is right here, 47.9. Divide that out and it comes out to be 0.0676. Oxygen is here, 16. Divide that out and it comes out to be 0.135. So percent to mass, mass to mole, divide by small, 0.0676, 0.0676. So we know we have Ti is 1. 0.135 divided by 0.0676 is approximately equal to 2. So it's TiO2 is your final answer. And that's how you get the empirical formula from the percent composition.